Hello, welcome to the course on 3G, 4G wireless communication systems. In the last lecture, we wrapped up our discussion on the Okumura model, and we were looking at the example of the Okumura model, and we said in that example scenario at a distance of 8 kilometers, carrier frequency 2.1 gigahertz and other parameter values, the path loss is 167 dB, what is what we computed. Then we moved on to the Hata model, and we said the Hata model is another popular model similar to the Okumura model, except it gives an analytical formulation to the graphical Okumura model, where the Okumura model uses a lot of graphs and so on. And we said we consider the same example using the Okumura Hata model, and we said the path loss is 165 dB, which is essentially close to what is predicted by the Okumura model. And then we moved on to something more important in a cellular system, which is the log normal shadowing. We said even at the same distance at several different points in a cellular system, the path loss is not same because of the shadowing effects, that is because the user might be, or the mobile user might be present behind a large wall or a large building or an obstruction and so on. Hence the shadowing, hence the net signal strength received at a location looks like a random, it is random in nature, with the mean or the 50th percentile signal strength predicted by the Okumura or Hata model, and the essential random deviations. There are random deviations around this mean signal strength. This is termed as log normal shadowing. In fact, we said that this factor, which is the log normal shadowing factor, this can be expressed as a Gaussian random variable with variance sigma square. It is log normal because this x sigma is in dB, hence the logarithm of the power is normal, hence this is a log normal random variable. And we also looked at the other important thing in this log normal fading. If I look at the distribution, it looks like a distribution with mean at the 50th percentile or the mean path loss and a random spread around this thing. And we said if you want to compute the probability that the path loss is greater than a certain threshold gamma, then I have to use the properties of the Gaussian distribution, and that is nothing but path loss, mean path loss plus this x sigma, which is a Gaussian random variable which is 0 with x sigma, which has variance sigma square is greater than gamma, which means x sigma is greater than gamma minus PL50, and the probability of that is given by the Gaussian Q function, which is Q of gamma minus PL50 minus mean path loss by sigma. This is the probability that because of log normal shadowing, the probability that the path loss is greater than this threshold gamma. Let us start from here and continue this discussion. We said that the probability that the path loss, actual path loss is greater than threshold gamma is nothing but Q, that is the Q function of gamma minus the path loss divided by sigma. Okay. This is the probability that path loss greater than threshold gamma. Hence, this is the probability that the path loss is greater than the threshold gamma. Let us consider an example. Let us, to understand this better, let us consider an example. What I want to consider this example is I want to consider the same model that we had used in the previous example. That is, I want to consider the previous example, used in the Hata model, where path loss or the 50th percentile path loss, where the 50th percentile path loss was given as 167 dB. Now consider log normal shadowing. Let the deviation sigma of the log normal shadowing be given by x sigma equals 6 dB. So, we are considering a log normal Gaussian random variable for the log shadowing with a deviation that is sigma equals 6 dB. So, sigma equals 6 dB, that is the deviation of the log normal shadowing factor, and we said the 50th percentile path loss is 167 dB. Now, employing these two facts, we would like to compute the threshold gamma such that the path loss is greater than gamma only 5% of the time and the path loss is less than gamma 95% of the time. So, what we want to do is we want to compute the threshold gamma such that the actual path loss PL is greater than gamma only 5% of the time or locations in the cell, which in other words is the same thing as saying 95% of the time / locations it is lower than this threshold gamma. That is in other words 95% of at 95% of the locations path loss is less than the threshold gamma. That is, we are setting this as follows. We are saying that our distribution looks like this, where the median path loss is 167 dB, that is the median path loss, and we want to compute this threshold gamma such that most of the time our observed path loss with this probability is less than gamma, and with this small probability it is greater than gamma, and this probability is nothing but we are saying 5%, and 95% of the time it is less than this threshold gamma. So, if I were to draw this, 95% of time it is less than gamma and only 5% of time it is greater than gamma, because this is the path loss which is a random variable and this is the distribution of that random path loss. This is the distribution of the random path loss. Hence, from what we have derived in our earlier discussion, we said that this probability that the path loss is greater than gamma is nothing but Q function of gamma minus the 50 percentile path loss divided by sigma equals 5%, that is greater than the threshold only 5% of the time, which is essentially 0.05, which essentially also implies that gamma minus the 50th percentile path loss by sigma equals Q inverse 0.05, which is essentially 1.65. The skew function is the Q function, that is the value of the Q function for different values, is tabulated in the form of tables. From those tables you can read this value Q inverse of 0.05. Alternatively, this can also be computed in MATLAB. So, this Q function is computed from the tables, all right. Hence, we can also write from this expression here, we can also write that gamma equals the 50th percentile path loss plus sigma times 1.65. We know both these quantities. The 50th percentile path loss is 167 dB plus sigma is given as 6 dB. So, this is 6 dB times 1.65. This is equal to approximately equal to 167 plus 10, which is equal to 177 dB. Hence, it is said that what this example essentially says is that even though the percentile path loss, the 50th percentile path loss is 167 dB, because of the spread or the randomness, 50%, it is only, this is less at 50% of the locations it is greater than 167 dB, and 50% of the locations it is less than 167 dB. So, if you want that additional reliability, that it is only greater than a certain threshold only 5% of the time, that threshold is not 167 dB, but 177 dB. That is, you can claim, that is, if you want to account for your path loss such that the path loss is greater than this threshold only at 5% of the locations, then you have to transmit an additional 10 dB of power. This is nothing but this is termed as the margin, where this margin is essentially arising because of the random shadowing factors, arising in fact because of the log normal shadowing in the system. Hence, now we can claim that the path loss is greater than 177 dB only 5% of the time. Hence, in this scenario, the path loss is greater than 177 dB only 5% of time. Hence, the path loss is greater than 177 dB only 5% of time. Another way of saying is, this is path loss is less than 177 dB 95% of the time. So, it is greater 5% of the time, which means rest of the time it is lower, which is the same thing as saying 95% of the time it is lower than 177 dB. Hence, in other words, path loss is lower than 177 dB 95% of the time, which means this 95% is also nothing but this is the reliability rho. Which is equal to 0.95. So, we can say the outage, which is the chance that the path loss is greater than 177 dB, is 5%, which is 0.05. In other words, the reliability, which is that the path loss is less than this threshold, is 177 dB, which is nothing but 95% or 0.95. And in terms of reliability, the margin required in general if rho is the required reliability or the desired reliability, the required margin, the desired margin is given as sigma q inverse 1 minus rho. This is the margin, which in the previous example again amounts to the same thing. This is 6 times q inverse 1 minus rho, rho is 0.95, therefore, q inverse 1 minus rho is q inverse 0.05, which is exactly 6 into 1.65 is approximately 10 dB. So, you can think of it two ways. You can either think of it as path loss greater than a certain threshold or path loss lower than that threshold with 1 minus that probability, which is essentially nothing but the reliability. So, there are two ways to think about it. One is outage, which is the path loss is greater than threshold. The other is reliability, which means path loss is lesser than that threshold, and the sum of both these probabilities is 1 essentially. Okay. So, that is essentially the log normal shadowing aspect of this thing, which essentially shows that if you want to account for the randomness in the shadowing factor around the cell because of large obstacles such as buildings and walls and large shadowing objects, then you have to transmit an additional power, which is essentially nothing but the accounts for the log normal shadowing, and that is also termed as the margin in this cellular system. Okay. So, now we move on to the next topic, which is actually the one of the most important parts in the cellular at the cellular receiver, which is essentially to characterize the noise process. So, the next aspect we want to tackle is nothing but the receiver noise computation. Receiver noise is nothing but the thermal noise that is present at the receiver. This arises due to the thermal noise, due to the thermal or essentially the Gaussian noise, what we model as Gaussian noise at the receiver, and this is an important one of the important distortions, or it is essential to characterize the noise at the receiver to accurately model the signal to noise ratio at the receiver. It is important, it is in fact critically important very important to accurately characterize noise power to compute the signal to noise power ratio that is, the use of this noise power is obvious because we want to compute the signal to noise power ratio at the receiver. Everything at the receiver, that is the accuracy of decoding and so on, depends on nothing but the signal per ratio of the signal power to the noise power. The signal power we can compute from the transmit power, path loss and so on and so forth. The noise power, which is the remaining part, has to be characterized accurately to characterize this signal to noise power ratio. And the expression for this signal to noise power ratio, this is given first characterized in two steps. First is known as the noise power spectral density. The noise this is the noise power spectral density, simply abbreviated as PSD, which as the name suggests means essentially that what is the density of the noise per hertz, that is, this is nothing but the noise power per hertz of bandwidth. Hence, naturally, if this noise power spectral density is denoted by eta, total noise power, since this is noise power per hertz, total noise power is nothing but this density into the total bandwidth B. Hence, total noise power equals eta naught into B, where eta naught is the noise power spectral density and B is the eta noise is the noise power spectral density and B is the bandwidth of the system. Knowing the noise power spectral density and the bandwidth of the system, I can compute the total noise power. And the noise power spectral density, the expression for noise power spectral density eta naught is given as follows, that is nothing but K T F, where of course the left is the noise power spectral density. What I have on the right are first K, which is equal to the Boltzmann constant, then I have T, which is nothing but the temperature in Kelvin, and I have F, which is essentially nothing but this is the noise figure. This is the noise figure, hence this is the net standard expression for the noise power spectral density, which is essentially eta naught. The noise power spectral density is nothing but K T F, where K is the Boltzmann constant, T is the temperature in Kelvin and F is the noise figure. And this K has a standard value, that is the Boltzmann constant, which is essentially 1.38 into 10 power minus 23. This is the value of the Boltzmann constant K. For instance, let us consider this example. Let us now consider this example. Compute noise power at 293. Compute the noise power at a temperature of 293 Kelvin and noise figure F equals 5 dB. Also the bandwidth B is equal to what we are asked to do is essentially we are asked to compute the total noise power in this system where the bandwidth is 30 kilohertz, noise figure is 5 dB and the temperature is 293 Kelvin. So, this again we have to proceed in two steps. First we have to compute eta naught, which is the noise power spectral density, multiply this noise power spectral density by the bandwidth to get the total noise power. Hence, what we have here is eta naught. First, let us compute this F in dB. F in dB equals 5 dB, which means F is nothing but 10 to the power of 0.5 in linear values. Hence, remember eta naught equals K T F. K is the Boltzmann constant, which is given as 1.38 38 into 10 power minus 23 into the temperature in Kelvin, which is nothing but 293 Kelvin, into the noise figure, which is 10 to the power of minus 10 to the power of 5. This is K, this is T, this is F, and this product you can show is given as 1.28 into 10 power minus 20. Hence, log 10 log 10 eta naught is nothing but the noise power spectral density in dB, which is nothing but minus 199, and this is in dB watts per hertz. Remember, this is a power spectral density, so this has to be in watts per hertz. Further, we are taking the dB, so this is in dB watts per hertz, that is minus 199 dB watts per hertz. And now we also said that the noise power sigma n square equals eta naught into B, which is essentially 1.28 into 10 power minus 20. This is what we said is eta naught into 30 into 10 power 3 equals 3.84 into 10 power minus 16. Hence, 10 log 10 sigma n square, 10 log 10 sigma n square equals log 10 84 into 10 power minus 16, approximately equal to minus 154 dB. Hence, the noise power in this scenario is eta naught B, where eta naught is this 1.28 into 10 power minus 20, bandwidth B is 30 kilohertz, that is 30 into 10 power 3. This is nothing but the 30 kilohertz bandwidth, and the net noise power is 3.84 10 power minus 16. Convert this into dB value, that is minus 154 dB. Hence, this is nothing but the noise power in dB. So, the noise power in dB is what we are saying is minus 154 dB. Thus, we have computed the noise power in dB. So, we computed several aspects. Now, we looked at path loss, we looked at the 50th percentile path loss, we have looked at the margin that is required to account for log normal shadowing, we have looked at the receiver noise computation. Now, we have to put all of these aspects together, and that is known as the link budget analysis. That is, we have to budget for these different losses and gains in different parts of the wireless communication system. This is termed as the link budget analysis. So, the next topic we are going to discuss is the link budget analysis, and the link budget analysis we said is nothing but it is a budgeting of power for different aspects of the wireless communication system. So, link budget analysis, in fact the link budget of a wireless link is nothing but the systematic is a it is nothing but a systematic listing of power losses and gains of different intermediate components in in the So, the link budget analysis is nothing like a budget, it is a systematic listing of the different components and their associated power gains or losses in the whole of this transceiver chain, that is from the transmitter to the receiver, so that you can account for the power gains and the losses, so that you know how much transmit power is transmitted, how much transmit power is received and what needs to be done. That is, it is like a budget analysis for this link, alright. And so, let us list these different components now. So, I am going to write these as a table as follows. So, I am going to draw a table. In this table, I am going to first write its sign, if it is a gain or a loss. For instance, transmit power, the transmitter power is a gain, that is larger than the larger transmitted power, larger is the power received. So, obviously, it is a gain. So, I am writing a symbol plus here and the symbol is PT. Next, I am going to account for transmit antenna gain. This is GT, this is the transmit antenna gain. Now, I am going to from this subtract the median link propagation loss, hence I am going to subtract the median now this is a loss. So, I am going to subtract this is L50. Then I am going to also subtract the margin. Remember, if we want to improve the reliability, we said we need an additional margin. So, I need to account for the margin also. I am going to subtract this margin in dB. Then at the receive antenna, I have a gain because of the receive antenna. So, that I am going to write as plus, because it is a gain. This is the mobile receive antenna gain. Receive antenna gain is GR. Then from this I subtract the cabling losses, because their losses, cabling losses which are L or C. Further to this I am going to subtract receiver noise power and also interference. Hence, I am going to subtract remember, there is a noise power at the receiver arising due to thermal noise. There is also interference from other users. Remember, we looked at systems like CDMA, where the other users cause interference to the desired user. Even in fact, in OFDM, where there is loss of frequency or there is a frequency offset. Hence, we said we are going to look at signal to not noise power, but signal to interference plus noise power ratio. Hence, this is characterization of noise and interference power, which we are subtracting. This is n plus I, and that I have is equal to the required SNR, which is nothing but the SNR required. So, what we have here is the path loss plus the transmit antenna gain minus the link loss minus the margin plus receive antenna gain minus cabling losses minus noise and interference is equal to the required SNR. This is nothing, this is essentially nothing but a simplistic representation of the link budget, which is essentially the losses and gains of the different components in this transceiver chain. And we can also express this, hence essentially writing this down. Hence, this gives the relation transmit power in dB plus gain of transmit antenna in dB minus 50th percentile path loss minus margin in dB plus gain of receive antenna in dB minus cabling losses in dB minus noise plus interference in dB equals SNR required of course in dB. So, this is the first link budget expression, this is the link So, SNR required is nothing but transmit power plus transmit gain minus path loss minus margin minus plus gain of receive antenna minus cabling losses minus noise plus interference power. Flipping this on its head, that is writing it in another way, this can also be recast to compute the required transmit power now as the above expression can be recast to compute required transmit power. It can be recast to compute the required transmit power as follows, that is SNR required is now SNR required, that is I move all these terms onto the right side except PT, which is the transmit power. Hence, I have SNR required plus N plus I dB plus LRC dB minus GR dB plus M dB plus L50 dB minus GT dB equals the required transmit power PT in dB. This is another way to compute the required transmit power. This is nothing but the required transmit power in terms of the different losses and gains in the system. Hence, this is the required transmit power in terms of the how to budget for this in terms of the required in terms of the different components in from the transmitter to the receiver. Let us do an example to understand this better. Let us do an example to put everything together. In fact, let us consider the scenario that we have described previously. Consider the previously described scenarios. If we look at the previously described scenarios, we consider, that is we consider D, which is the distance equal to the cell radius equals 8 kilometers. We consider the carrier frequency FC equals 2.1 gigahertz. We consider transmit antenna height equals 40 meters and the receive antenna height equals 2 meters. This is similar to what we consider in the Okumura model. FC is the carrier frequency, D is the distance, HT equals the transmit antenna height, HRE equals receive antenna height. Let me just write this again. This is the TX antenna height and this is the RX antenna height. Okay. And we require a reliability we require a reliability of 95%, the temperature is 293 Kelvin. This is what we had seen in the noise computation example, and the bandwidth B equals 30 kilohertz, noise figure equals 5 dB, and here I have to add that when we require reliability of 95%, the variance of the log normal shadowing is similar to what we considered earlier, that is variance sigma equals 6 dB. Sigma is nothing but the variance of the log normal shadowing. This is nothing but a deviation. This is not the variance, but this is the deviation of the log normal. This is all that we have considered previously in the previous examples. Now, we have some additional information. Also consider the following additional information. The following additional information is given, that is RX antenna gain is 5 dB, cabling losses equals 3 dB, the Tx antenna gain equals 12 dB, and the noise power, it is given that the interference power is equal to the noise power. So, the interference power I is equal to the noise power, and what we have to compute is, it is asked to compute, employing the information above, we want to compute the transmitter power required employing the above information, compute the transmitter power required for a bit error rate for a BER, which essentially stands for bit error rate equals 10 power minus 4 for BPSK at the. So, what is being asked is obvious, that we have, this is a kind of a long problem statement. What we have given here is, we have given information about a list of items, and what we are now being asked is, essentially in this wireless cellular system, characterize or compute the transmit power required at the transmitter or the base station, such that at the receiver I have enough power or signal to noise power ratio, so that I can decode BPSK transmission at bit error rate of 10 power minus 4. So, that is the requirement of the problem, which is to compute the transmit power using these different components of the link budget. Hence, naturally we have to use the link budget analysis. Let us start with what we already have. We already know from the previous examples that so let us start the solution from previous example. We know at d equals 8 kilometers and Fc equals 2.1 gigahertz and HTE equals 40 meters and AHRE equals 2 meters. We know, and we computed it using both the Okumura and the Hata models. We know that the L50 or the 50th percentile path loss in dB is 167 dB. This is the first piece of information. We know that at distance 8 kilometers 2.1 gigahertz and this transmitter and receiver heights, the path loss is nothing but 167 dB. Then we also know that for 95% reliability, the margin required is 10 dB, that is what approximately 10 dB, that is what we computed for the margin required is 10 dB for 95% reliability. That is, we said this is nothing but corresponds to rho equals 0.95. This is computed at 95% reliability, that is rho equals 0.95. The required margin, which is nothing but mdB, is 10 dB. Further, we computed that the noise power at 293 Kelvin and bandwidth of 30 kilohertz is eta naught b, which is equal to 3.84 into 10 power minus 16, and we are also given that interference power is equal to noise power. Given that interference power is equal to noise power, implies I is also equal to eta naught b equals n equals 3.84 into 10 power minus 16. It is given in the problem that the interference power equals noise power. The noise power we already computed at the given parameters, that is 293 Kelvin and noise figure 5 dB is 3.84 into 10 power minus 6, hence interference power is also equal to noise power, which is equal to 3.84 into 10 power minus 6, which now means n plus I is nothing but twice 3.84 into 10 power minus 16, and computing this value in dB, this is nothing but minus 154 plus 2 factor 2 corresponds to 3 dB, which is essentially minus 151 dB. Hence, the noise plus interference power in dB, this is nothing but noise plus this is nothing but the noise plus interference power required, noise plus interference power in dB, which is nothing but minus 151 dB. Now, let us compute another aspect, which is the required SNR. We are told that SNR required should be enough to support BPSK decoding at 10 to the power of minus 4. Hence, or the required SNR for BER equals 10 power minus 4 with BPSK remember, in the early part of the class we derived the expression for bit error rate for BPSK, and that bit error rate is nothing but half into 1 minus SNR by 2 plus SNR. Now, we require a bit error rate of 10 power minus 4, which means we can write 10 power minus 4 equals half into 1 minus SNR by 2 plus SNR. Now, rearranging the terms, we can write SNR by 2 plus SNR equals 1 minus 2 into 10 power minus 4 square. Hence, I can also write SNR, the final expression for SNR is twice 1 minus 2 into 10 power minus 4 whole square divided by 1 minus 2 into 10 power minus 4 whole square, which is essentially approximately equals 5 into 10 power 3. Hence, the SNR required, this is nothing but SNR required, which is essentially SNR required for 10 power minus 4 bit error rate in BPSK. Hence, SNR required in dB is 10 log 10 5 into 10 power 3. This is nothing but 37 dB. Hence, the SNR required in dB is nothing but, this is nothing but the required, this is nothing but the required SNR in dB. Now, we put all these things together in the link budget. Hence, we can formulate the link budget as follows. I am going to again draw the table. First, we have the transmit power PT. Remember, this transmit power is unknown. This is what we have to compute. Transmitter power PT, this is plus transmit antenna gain GT. Remember, this is given as 12 dB. If you look at the problem information, this transmit antenna power gain is given as 12 dB plus minus median propagation loss is 167 dB minus the margin required, path loss is 167 dB and minus margin we said is 10 dB, and we have mobile antenna gain or the receive antenna gain, which is essentially the receive antenna gain, which is essentially 5 dB, and then we have cabling losses minus cabling loss, which is 3 dB. Further, we have receiver noise plus interference, which is given as minus 151 dB, and that should give us the required SNR, which is nothing but what is required for BER decoding or BPSK decoding with bit error 10 power minus 4, and that we said is 37 dB. Hence, we have written all the components in our link budget. What is remaining is to compute this transmit power PT. Due to lack of time, I am going to stop it here at this point, and the next time when we return, we are going to complete this example and move on to the next topic. Thank you very much.